Hello and welcome to this new tutorial. Now we're about to build the RNN part of the MDN RNN model. And what we're going to start with is to introduce all the parameters, the parameters that will be required to build the RNN. And the first one that we're going to introduce right now is the number of mixtures used to, sample that probability of the next latent vector conditionally to the current latent vector, the action plate, and the current hidden state. And that number of mixtures is clearly given in the article, again in that section of the appendix, because indeed in both tasks, meaning the car racing task and the Doom task, well, the author used 5 Gaussian mixtures. And so the parameter we're about to introduce right now is exactly that number of mixtures. And so the name we're going to give for that parameter, and we're actually going to create an object variable, which will be a variable of the MDN RNN instances of this class, will be self.numMixture. And we could initialize it to 5 right now, but the way we're going to do this is rather through the HPS object parameter that we have as the argument of the build model method here, because indeed it contains all the hyperparameters of the MDN RNN model, including the number of mixtures. And therefore, to initialize this way, we're going to call our HPS object, from which we're going to get that number of mixtures, which has the same name, numMixture. Alright, perfect. And then we're also going to create a separate variable, but this time not attached to the object, and that we're going to call kmix. So I'm just taking the same variable names as the author's implementation, because the author's implementation is larger. So if you want to develop this code to use it differently, to perform some, for example, other training, well, I prefer to keep the same names for the parameters and variables as the author. So kmix here, and this is going to be equal as well to that number of mixture, self.number of mixture. So I'm just copying this and pasting that here. All right, so that was for the first important hyperparameter of the RNN. And now we're going to introduce and initialize 2 other essential parameters of the RNN, which are, of course, the dimension of the input and the dimension of the output. So let's first give the names of these parameters. The dimension of the input will be in width, and the dimension of the output will be out width. And that's also the number of channels in respectively the input and the output. And so what are going to be these dimensions? Well, let's have a look at our cheat sheet. This is our cheat sheet, and right now we're building the MDN RNN. And as we can see, the MDN RNN model here in the full world model actually has a double input. It has a first input coming from the latent vector z returned by the VAE, and also a second input coming from the action returned by the controller, right? You can see that the controller plays the action inside the environment, but not only that, it also returns that same action into the MDN RNN. And therefore the MDN RNN has a double input, z and action. So now the question is, what is the dimension of z and what is the dimension of the action? Well, the dimension of z, we already know that it is z size, because if we go back to our code in our VAE, we can see that z here has the same dimension as mu and sigma, because this is a sum of 2 dense layers. And since both of these dense layers have a number of elements equal to z size, and z size is equal to, by default, 32, then the dimension of the first input z here will be z size, equal to, by default, 32. And this is actually confirmed in the article. I made this other page so that I don't have to scroll up. The dimension of the latent vector is indeed 32, right? This means exactly that it is a vector of 32 elements. And now that we have the dimension of z, what is the dimension of the action? Well, at each time the agent, and actually ourselves as well, because we're going to play the game too, we're going to race the car. Well, at each time there are 3 possible actions that can be played, which are, first, we can accelerate, second, we can slow down, and third, we can turn, left or right. And therefore, there are 3 actions that are played each time, or more specifically, each time step of the environment. And therefore, the action here is a 3-dimensional input. And so, the total dimension of the input of the MDN RNN is 32 plus 3 equals 35. And that's the number of channels we're about to introduce for this first input in width. And so again, here we could initialize this as 32 plus 3 or 35. But again, we're not going to do it this way. We're going to do it with our HPS hyperparameter object. And therefore, we're going to call HPS again here, from which we're going to get another attribute, which will be, of course, the attribute for that dimension of the input, and which will be named input underscore sec underscore width. So again, I'm just taking the same parameters names as the author. All right, now let's tackle the dimension of the output, out width. And so let's go back to our cheat sheet of the full world model. We can clearly see that this time we have a single output, which is the hidden state. And the hidden state has the same dimension as the other input, the latent vector z, and therefore it's going to be as well 32. And therefore, again, we're not going to initialize this as 32, but by taking our HPS parameter object, from which we're going to get this time the output sec width attribute, corresponding of course to the dimension of the output. So here I'm just replacing input by output. Perfect. And now one last parameter that we have to introduce, which is the length, and which will correspond to the maximum sequence length of an episode. In other words, the maximum steps in an episode. Remember when we played the car racing game against the powerful AI in the first tutorial of this course? Well, we played on 900 steps. This was written in the end in the console. And right now what we are about to initialize is just the maximum number of steps, which will be initialized as 1000. And that's of course for the training. You know, the RNN model will be trained on some episodes, which will have a maximum number of 1000 steps. And the reason why we have to introduce and initialize this parameter right now is because in the same build model method, we will implement the training operations. All right, so let's do this. Length, which again, we will initialize thanks to our HPS object parameter. So I can either take self.hps or just HPS like we did just above. That's the same because in the init method, we initialized self.hps as the argument HPS given when creating the instance of the MDN RNN class. So that's just the same. And from this HPS object, well, we're going to get the following hyperparameter, which is the max sec len. Max sec len, the maximum number of steps. All right, perfect. So we're done with the main parameters that we'll need to build the RNN. And now we're just going to introduce one last thing, which is the global step, right? The global step of the training operation, which is another parameter of the MDN RNN model. And so we're going to create a new object variable, which we'll call as well global step, as what we did for the VAE. But first, before we create it, we're just going to make sure that we are in the training mode. And actually the training mode is once again another hyperparameter of this HPS object. And so I'm going to call the HPS object again, from which I'm going to get that is training hyperparameter, which will tell us the mode, whether we are in training mode or in inference mode. And so if hps.isTraining equals true, which we don't have to specify because true is the default value of a Boolean, then what we can do is introduce and initialize the global step object variable. And since it is exactly the same as the one we introduced here for the VAE, right? Exactly the same. If self.isTraining equals true, then self global step will be created as an object of the variable class by TensorFlow with the exact same argument. So I'm just copying this, then I'm going to paste that inside our RNN model, and here we go. Now we can begin the creation of the RNN architecture. So we'll do that in the next tutorials because it's actually going to be a long code section. So get yourself some good energy and I'll see you as soon as you're ready. Until then, enjoy artificial intelligence.